Okay, go through the problem once. A rectangular prestressed concrete beam 150 wide and 300 deep is used over a span of 10 meter. Okay, cross section dimension is 150 by 300 that I have written in the diagram, and the length of the beam is given as 10 meter. L is equal to 10 meter. L is equal to 10 meter. Then the cable with zero eccentricity at support. Okay, at support eccentricity is 0 and linearly varying to 50 mm at center. Okay, here you can see the cable is linearly varying at 50 mm, 50 mm at center, 50 mm at center. Okay, carries an effective prestressing force of 500 kilonewton. P is given, that is 500 kilonewton. P is equal to 500 kilonewton. Okay. Find the magnitude of the concentrated load Q located at the center of the span for the following conditions. He says that concentrated load Q we have to find, which is located at the center of the span. Okay, for the following conditions. Okay, he has given two different conditions. In that first condition, if the load contracts the bending effect of the prestressing force, neglecting self-weight of the beam. Okay, if the load contracts the bending effect of the prestressing force, what should be the magnitude of the load? Okay, that is the first question. Second question is, if the pressure line passes through the upper kern of the section under the action of load, self-weight and pre-stress. I will explain you in detail by solving this question B. Okay, first we will solve for question A. Okay, question A. Question A is to find Q, magnitude of the concentrated force acting at the center of the beam when this load Q contracts the bending effect of force P. Okay, this is the first question. Okay, so this is similar to the previous question. What we have to do is, first we have to find bending moment due to prestressing force, then you find bending moment due to external load. Equating both the bending moments due to external load and the prestressing force, you will get the load required to contract the effect of prestressing force or bending moment due to prestressing force. Okay, that is what we have to follow to solve for P here. Okay, first you find the external bending moment. External bending moment will be equal to external bending moment will be equal to C. External bending moment, how we will find? External load is applied at midspan section, correct? Okay, it is applied at midspan of the beam, correct? So moment due to the simply supported beam carrying point force at the center of the span. What is the formula? WL by 4, correct? So I'll write it as QL by 4. QL by 4. QL by 4. WL by 4. Okay. This is external bending moment. Okay. Is equal to M Okay, this is external bending moment m is equal to QL by 4. Similarly, you find internal bending moment, that is moment due to pre-stressing force. Okay, about the center of the span only, about the center of the span only. Okay, therefore internal bending moment is equal to, okay, internal bending moment means what? Moment due to pre-stressing force P. Moment due to pre-stressing force P. Okay, about the center of the beam. Okay, because here we have found out moment at the center of the span QL by 4. Similarly, we have to find what is the internal bending moment due to pre-stressing force at the center of the, about the center of the beam. Okay, so what you do is you write components of this pre-stressing force P. Okay, horizontal component and the vertical component. Let me assume this angle as theta. Let me assume this angle as theta. So horizontal component will be what? Vertical component will be P sin theta. Horizontal component will be P cos theta. P cos theta. Okay. So here angle will be same only. Okay. Equal and opposite angle. Theta will be the angle here also. Now I want moment of this pre-stressing force about this point, center of the beam. Okay. So as the force P is inclined in nature, okay, or to make the easier calculations for finding the moment, what I have done is I have written components of the pre-stressing force, components of the inclined force, both horizontal component and the vertical component. Okay. Now first you find moment of horizontal component about this point, So P cos theta into perpendicular distance is 0 because the line of action of P cos theta is along this point only. There is no perpendicular distance of this point from P cos theta force. Okay. Then plus P sin theta, that P sin theta into perpendicular distance, how much? So P sin theta force, how it will act? It will act like this here at this point. So perpendicular distance is L by 2. Perpendicular distance of this point from line of action of P sin theta, it is L by 2. P sin theta into L by 2. Okay. Now M is equal to, first term is 0. P pre-stressing force, that value is known, 500 kilonewton. 500 sin theta into L, length of the beam, it is given 10 meter, 10 by 2 into 10 by 2. So 500 into 5, 10 by 2 is 5. So 2500 sin theta. You got the value as 2500 sin theta. Okay. Now we want the value of this sin theta, correct? We want the value of sin theta. So you take this triangle. You take this triangle A, B, C. Okay, you take this rectangle triangle ABC. Okay, in this rectangle triangle, if you measure sin theta, okay, if you measure sin theta is opposite by hypotenuse. Opposite is 50 mm. 50 mm divided by hypotenuse is BC is the hypotenuse. This is the hypotenuse, correct? From triangle ABC. Okay, from triangle ABC. Okay. Now we want the value of BC, correct? We want the value of BC. BC you can find because L by 2 value is known. How much is the L by 2 value? Total 10 meter. So 5 meter is the L by 2 value. Okay. So AC BC square will be equal to AC square plus AB square. Correct? AC square. BC square is equal to AC square plus AB square. Plus AB square. AC square plus AB square. AC square is AC length is 50 mm plus AB square is 5 meter. That also is substitute in terms of mm only. 5,000. 5 meter means 5,000 mm square. BC square. Okay. So BC is equal to root of this answer. So answer that you get is you will get around 5,000 only. Okay. 550 square plus 5,000 square. In terms of meter, 50 square root of 50 square plus how much? 5,000 square, na? 5,000 square. If you calculate root of 50 square plus 5,000 square. You can see that the answer is 5,000.24, almost equal to 5,000 only. Okay. So for that purpose, I'll take 5,000 mm only. BC is equal to 5,000 mm only. Okay. Because you can here you can see that there is depression of the cable of only 50 mm over a length of 5,000 mm. Okay. Therefore, almost this AB length will be equal to BC length only. Okay. So BC becomes equal to 5,000 only. Okay. BC becomes equal to 5,000 only. Therefore, sin theta is equal to, therefore, sin theta is equal to, here we have 50 by BC, 50 by 5,000 by this. You can substitute this value here directly, sin theta. Okay, so in this equation, therefore, m is equal to 2,500 into sin theta is what? 50 by 5,000. 50 by 5,000. Okay. Now m is equal to, you can calculate 2,500 into 50 by 5,000. 50 by 5,000 is this much into 2,500. So answer is 25. Okay. 25 kilonewton meter. Okay. Answer is 25 kilonewton meter. Okay. Now you can equate both internal moment and external moment to get the value of Q. Okay, to counterbalance the moment due to prestressing force. For balancing, you know, right? Therefore, for balancing, external bending moment should be equal to internal bending moment. Okay. The external bending moment is QL by 4. Okay. QL by 4 is equal to internal bending moment is 25 kilonewton meter. So Q into length is 10 meter divided by 4, it is equal to 25. By this we can solve for Q. If we solve for Q, it will be 10 kilonewton. Okay, so if you apply a concentrated force of 10 kN at the midspan of the beam, then it will counterbalance the moment due to prestressing force. That is the meaning. Okay, to this question A is solved. Question A is solved. Okay, now coming to the question B. Okay, if the pressure line passes through upper curve of the section under the action of load, self-weight and pre-stress, what is the magnitude of the prestressing force? That is the question. Okay, question B. Right. Question B is value of Q to find value of the load Q when the pressure line passes through upper curve of the section Okay, so before going to solve this problem, let me explain what is the meaning of this upper curve. Okay, I will go to the previous discussion. That is pressure line discussion. Yes. Okay. So here it is one new technical term we got, that is upper curve. Okay, upper curve, lower curve, like that we got one technical term. Let us understand what is the meaning of that. Upper curve means, here you can see, students, the force P is applied at a distance of E is equal to h by 6, at an eccentricity of E is equal to h by 6. Okay. So at this point, if you calculate the stresses, okay, if you calculate the stresses, the stress at one particular point is 0. Resultant stress at one particular point is 0. Similarly, if you apply the same force P here at the same distance, E is equal to h by 2. Okay, you will get the nature of diagram like this. Nature of diagram like this you will get. Means at bottom you will get the resultant stresses 0. Okay, when the force is applied above the neutral axis. Okay, so the region, okay, so the region where if the prestressing force is applied, the resultant tensile stress will be 0. Okay, the resultant tensile stress will be 0, is called as kern. Okay, this portion is called as kern. Okay, and upper point is called as upper kern point, and lower point is called as lower kern point. Okay, lower point is called as lower kern point. Okay, so this is the meaning of upper kern or lower, this is the meaning of kern. Okay, kern portion. I hope you understood. Here, while discussing the pressure line, what we have done is we have applied the prestressing force P at a distance of E is equal to h by 6. Okay, at that condition, if we calculate the resultant stress, so we will get 0. That calculation I have shown here. Okay, we got 0. Similarly, if you apply the same prestressing force at the point of at a distance of h by 6 above the neutral axis, you will get this kind of nature of stress. At the bottom, you get the stresses 0. At the bottom, you will get the stresses 0. Okay, so the current portion is the portion where if the prestressing force is applied, then we will get the resultant tensile stress as 0. Okay, you will get the resultant tensile stress as 0. That is the meaning. Okay, so moving to the question. Moving to the question, the value of, we have to find the magnitude of the force Q, point force, concentrated force Q, when the pressure line passes through upper kern of the section. Okay, pressure line, if the pressure line passing through upper kern of the section means the resultant tensile stress is 0. That is the meaning. Simple, students, remember. Okay, if he says that the pressure line pass through upper kern or lower kern, it is understood that resultant tensile stress is equal to 0. Okay, I hope you all understood about this kern. Okay, so still if you have doubts, you can if you need any clarification, you can ask. Okay, below you write the sentence. You write a sentence. If pressure line, if pressure line pass through upper kern of the section, pass through upper kern of the section, upper kern of the section, then the resultant stress, then the resultant stress resultant tensile stress, okay, resultant tensile stress is equal to 0, which is nothing but F inferior equal to 0. F inferior equal to 0. We know the formula for F inferior, that is P by A plus PE by Z minus mg by Z minus mq by Z is equal to 0. Okay. So this is what the condition we get from this statement. Okay, from this statement. Okay, now call this as equation number 1. Okay, you calculate all the required parameters. Okay, calculate all the required parameters and substitute in this equation. You will get the moment due to live load. Okay, knowing moment due to live load, you can calculate the concentrated force Q. Okay, now P is equal to, it is given in the problem only, how much it is given, prestressing force P is equal to, it is given as 500 kilonewton, 500 kilonewton, nothing but 500 into 10 power 3 Newton, cross sectional area A, you can calculate it, the dimensions are given, it is 150 by 300, 150 by 300, 45,000 mm square. Then what else? Eccentricity is needed, correct? Eccentricity is given in the problem only. Okay, what is eccentricity here? 50 mm. 50 mm. 50 mm. Then section modulus Z is equal to I by Y. Okay, nothing but BDQ by 12 divided by D by 2. Okay, you can substitute the values or you can simplify this. If you simplify, you will get BD square by 6. Nothing but B is 150 into 300 square by 6. How much you'll get? Section modulus. Check the answer. 2.25 into 10 power 6 mm cube. 2.25 into 10 power 6 mm cube Z. Then what else is required? Moment due to dead load mg is required. First you calculate the dead load moment mg. First you calculate the dead load intensity. Dead load is equal to cross-sectional area divided by density. Cross-sectional area is 45,000 mm square. Nothing but 45,000 into 10 power minus 6 meter square. So 45,000 into 10 power minus 6 density of concrete is 24. So dead load intensity WQ is equal to, so we will get it as 13.5 kilonewton. Sorry, it is 1.08 kilonewton per meter. 1.08 kilonewton per meter is the dead load intensity. If you know the dead load intensity, you can calculate the moment. Therefore, moment is equal to WG, this one, WG L square by 8. WG is 1.08. Length of the beam is 10 meter divided by 8. Therefore, mg is equal to 13.5 kilonewton meter, or 13.5 into 10 power 6 Newton millimeter. Okay. Now you can substitute everything. You will get the MQ. Okay. P is equal to 500 into 10 power 3. Equation 1 becomes, therefore, equation 1 becomes P by A. P is 500 kilonewton, 500 into 10 power 3 Newton. Area is 45,000. Then plus P by Z, 500 into 10 power 3. Eccentricity is 50 mm divided by section model of Z is how much? It is 2.25 into 10 power 6. 2.25 into 10 power 6. Then minus mg by z. Mg is 13.5 into 10 power 6 divided by 2.25 into 10 power 6 minus mq by z. Minus mq by z is equal to mq by z is 2.25 into 10 power 6. 2.25 into 10 power 6 is equal to 0. Okay. Now you know the formula for MQ. What is the formula for MQ? Live load moment. Live load moment, it is QL by 4. Okay. We know that MQ is equal to QL by 4. MQ is equal to QL by 4. Okay. Q, you keep as it is. Length of the beam is known. How much it is? 10 meter divided by 4. So 10 by 4 is 2.5. It becomes 2.5 Q. Okay. Therefore, MQ is equal to 2.5 Q. Okay. Now this equation we can rewrite as same terms. First three terms are same. 500 into 10 power 3 divided by 45,000 plus 500 into 10 power 3 into 50 divided by 2.25 into 10 power 6 minus 13.5 into 10 power 6 divided by 2.25 into 10 power 6 minus mq is nothing but 2.5 load q divided by 2.25 into 10 power 6 is equal to 0. So in this equation only q is the unknown parameter that you can solve. If you solve, you will get the answer as okay. If you solve for q, we will get the answer as 14.6 Newton. All of you calculate and cross check the answer. Okay, we'll get the answer as 14.6 Newton. Okay, so this completes the problem. Okay, Any doubts you can ask. Okay. Now we'll move on to the next problem. Fourth problem. A concrete beam with a overhang is simply supported at A and B for a span of 8 meter. It is a overhang beam. And the length of overhang is 2 meter. The beam is of rectangular section, 300 mm wide, 900 mm deep. Sectional dimensions are given, and UDL is acting on the beam. Intensity of UDL is also given, 3.52 kN per meter. Okay. The question is to find the profile of the pre-stressing cable with an effective force of 500 kN. Okay, which can balance the dead load and live load on the beam. Okay. First, all of you write the question. Write the question, all of you. Okay. Once again, go through the problem. Concrete beam with overhang is simply supported at A and B over a span of 8 meter. And the overhang BC is 2 meter. There is a beam ABC. Okay. At A and B, there are simple supports, and portion BC is overhang. For that, I'll write the diagram.
Sir, question.
Yes, yes. Question not written. Huh? You want time?
Yes, sir.
Yes, yes, right. Okay. I'll write the diagram for the overhang beam which is given in the problem. I hope you have written the question. What it says? Uh, the concrete beam with a single overhang is simply supported at A and B. At A and B, the beam is simply supported and the overhang is BC. The BC, the remaining length of the beam, BC is, it is a overhanging portion. Okay. The beam is of rectangular section 300 mm by 900 mm deep. That I have written in the cross-sectional diagram. Supports a uniformly distributed live load of 3.52 kN per meter over the entire length, in addition of self-weight. Okay, this load is inclusive of the self-weight. Okay, no need to calculate self-weight once again. Okay, so it carries an UDL of how much? 3.52 kilonewton per meter. 3.52 kilonewton per meter. Determine the profile of the pre-stressing cable with an effective force of 500 kilonewton, which can balance the dead load and live load on the beam. Okay, it is similar to the first problem that what we solved. Okay, we have to uh, find a suitable cable profile. We have to suggest a suitable cable profile. To suggest a suitable cable profile, what we need? We need what is the bending moment diagram for the beam. What is the actual bending moment diagram for the beam? Okay, first, so in the very first step, what you have to do is first you need to find what is the bending moment diagram of the beam. Referring to the bending moment diagram, you can suggest a suitable cable profile similar to the bending moment diagram, but opposite to, but in opposite direction. Correct. Now, so here you do one thing. Here in the problem, in addition to itself, it is there, no? You do one thing here. You change as exclusive of self-weight because what happened now here in my calculation excluding the self-weight I have done because to cross-check the answers we'll take the same condition. Okay, you change the question as exclusive of self-weight. Okay, if he says exclusive of self-weight, then you need to calculate the self-weight and add it to the live load. Okay. Now you calculate the self-weight of the beam. Self-weight of beam is equal to cross-sectional area into density. Cross-sectional area is 300 by 900 in terms of meter square, it is 0.3 into 0.9, correct? Into density 24. If you calculate, so you'll get the answer as 6.48 kilonewton per meter. And live load on the beam is given. Live load on beam is given. How much it is given? It is given as 3.52. 3.52 kilonewton per meter. You can calculate the total load. Total load is equal to 6.48 plus 3.52. Exactly, we'll get 10 kilonewton per meter. Correct? 10 kilonewton per meter. So the total UDL that will act on the beam is 10 kilonewton per meter. Change the value here. 10 kilonewton per meter. Okay. Now, for this loading condition, you find the bending moment diagram first. Find the bending moment diagram first. How we will find the bending moment diagram? See, this is a beam with it is a different beam with UDL acting on it. You need to follow the first principles to find the BMD. Okay, you draw a dotted line along the support points so that it will be easy for you to write the BMD. Okay. How will find the BMD? First, you find the reactions at the support. Okay. So to find the reaction at the, you cannot directly find the reaction at the support because the loading is unsymmetric. Okay. Loading is unsymmetric. If it is symmetric loading, total load divided by 2. Divided on it. Because of unsymmetric loading, you need to find it by using equilibrium equations. Right? First, you use sigma fx or sigma fh equal to 0, sum of forces in horizontal direction equal to 0. There is no forces acting in horizontal direction, all are in vertical direction. Leave this condition. Go for the next condition. Sum of forces in vertical direction equal to 0. Sigma fv equal to 0. So let me call reaction at A as RA, reaction at B as RB. Okay. Therefore, plus RA minus UDL, which is acting throughout the length of the beam. Okay. So here span is 8 meter, correct? 8 meter is the simply supported span and plus 2 meter overhang. 8 meter is the simply supported span plus after this 2 meter overhanging portion. So RA plus RA minus 10 kilonewton per meter acting over a length of 10 meter. 10 into 2. Sorry, 10 into 10 meter minus 10 into 10 plus one more reactive force RB. RB equal to 0. Therefore, RA plus RB is equal to 100 kilonewton. Okay, call this as equation number 1. Then apply the last condition, sigma MA equal to 0. Sigma MA equal to 0. Sum of moments of forces about point A equal to 0. That is the meaning. Okay. So moment of this RB about A is how much? RB into perpendicular distance 8 meter. Okay. And this RB will cause anti-clockwise moment about point A, sign is minus. Then plus moment of this UDL. Moment of this UDL about point A. Okay. First you convert this whole UDL into point load. So 10 kilonewton per meter, it is acting over a length of 10 meter. So 10 into 10. So now it is converted into point load into perpendicular distance 10 divided by 2. Length divided by 2. Okay, why the sign is plus? This UDL will cause a clockwise moment about point A. That is why sign is plus. Is equal to 0. Okay. By this you will get the value of RB. If we calculate, you will get it as 62.5 kilonewton. Please check the answer. Now, if you get the value of RB, you can calculate the RA, substituting in this equation 1. Therefore, equation 1 becomes RA plus 62.5 is equal to 100. Therefore, RA is equal to 100 minus 62.5. How much? 37.5 kilonewton. Now you got reactions at the support. write those reactions here. RA is equal to 37.5 kilonewton and RB is equal to 62.5 kilonewton. Okay, 62.5 kilonewton. Now what is next step? Next step is to find the bending moment values. Okay, so before going to find the bending moment values, you also find shear force values. Okay, why? I'll tell you later. Okay, I'll tell you later. First you find shear force values, SFD. The purpose of finding this SFD I will tell you later. Okay, first you find shear force at A. Shear force at A is equal to how much? Shear force at A is 37.5. 37.5 kilonewton. Then we have one more point B. Okay, and UDL is acting throughout the length ABC. Okay, so while finding shear force values at B, you need to find shear force at LHS of B and shear force at RHS of B. Okay, first you find shear force at left of B. These are all basic things that you already learnt in your third semester strength of material subject. Shear force at LHS of point B is equal to sum of forces on the LHS of B, okay, plus 37.5 minus 10 into 8 meter. 37.5 minus 10 into 8. Okay, so answer is minus 42.5 kilonewton. Then you find shear force at RHS of B. Okay, RHS of B means including this reaction at the B, you need to calculate the shear force. LHS of B means excluding this reaction at B, you need to calculate the shear force. So it is minus 42.5 plus including reaction at B is plus 62.5 plus 62.5. So answer is 20 kilonewton. Okay. Similarly, if we calculate shear force Similarly, if we calculate shear force at the last point C, shear force at C, if we calculate, you will get 0 only. Okay, you will get 0 only because it is a free end. There won't be any shear force. Okay, it is a free end. If you want, you can calculate. Otherwise, you can directly put the answer as 2, as 0. So shear force at C will be 20 minus means previous shear force at B minus the force acting over length BC, 10 into 2. 10 into 2. So you get to 0 only. Or else you can directly put the answer as 0. Okay. Now write the shear force diagram. Now write the shear force diagram using these shear force values. All of you write the shear force diagram. Have you written the shear force diagram, students? Write the reference line. Okay. Shear force at A, how much we got? Shear force at A plus 37.5 plus 37.5. Okay. Then shear force at LHS of B, we got it as minus 42.5 below the axis, below the reference axis, minus 42.5. Then shear force on RHS of point B plus 20. Plus 20. Then shear force at last point is 0. Now join all the points. Okay. So here you've drawn the SFD. See here when we draw on the SFD, there is shift of SFD from positive to negative, correct? There is shift of SFD from positive to negative. Okay. So at this particular point, no, bending moment will be maximum. Okay. Bending moment will be maximum where the shear force is 0. Where the shear force is 0. That is why I asked you to draw the SFD. Okay. Therefore, at this point also, while finding the bending moment, at this point also, we have to find the bending moment. Okay. So we don't know the what is the uh, distance of this point where shear force is 0 from the left support, correct? So let us assume that distance as x. Let us assume that distance as x. Okay. Now, if this is a x, overall distance from A to B is 8 meter. Thus, this distance becomes 8 minus 6. Okay, 8 minus x. Now, we can find what is the value of x. Now, you consider this triangle and one more triangle here. Both are similar triangles. Applying the similarity rule, you can find the value of x. Correct? Yes, who is that? Someone is speaking. Okay. Okay, below you write a sentence, let point where shear force is 0 and bending moment is maximum be at distance x from A. A distance x from A. Okay, this is the point A. Now apply the rule, similarity rule between both the triangles. Here height of this first triangle is 37.5 divided by base width is x. Let me take as the ratio of 37.5 divided by x is equal to, okay, you take the right triangle, one more triangle below the reference axis, that is its height is 42.5 divided by base width is 8 minus 6. 42.5 divided by 8 minus x. Okay. Now if you solve for x here, you can write it as 37.5 divided by 42.5 is equal to take this x to the RHS, x divided by 8 minus 6. Okay, so this value will be 0.8823 is equal to x by 8 minus x. So if you multiply this 0.8823 to the 8 minus x, means if you take this 8 minus x to the LHS, it will be 7.058 minus 0.8823x is equal to x. By solving, you will get the x as 3.75 meter. Okay. Shear force is 0 which means that shear force is 0 at a distance of 3.75 meter from left support. So while finding bending moment, now you need to find the bending moment at this point also. Okay, you need to find bending moment at this point also. Let me take this as x, cross section as x. Okay, this point x. Okay, now you can find the bending moment values. Bending moment values when BMD. Okay, you can find the bending moment at each and every point. Bending moment at A equal to how much? Bending moment at A is 0 because it's some simply supported beam, simple support. At that point, bending moment is always 0. Okay, then where else we will to find bending moment? Bending moment at x equal to 3.75. Moment at x is equal to, okay, means at a distance of 3.75 meter, we need to find the bending moment. First, you find bending moment due to RA, that is 37.5 kilonewton. 37.5 into 3.75, 37.5 into 3.75 minus moment of UDL about the same point. 10 into 3.75 into 3.75 divided by 2. And it is anti-clockwise moment, that is a minus sign. 10 into 3.75 minus into 3.75 divided by 2. Okay. If you calculate the answer, it is 70.31 kilonewton meter. Okay. Then you find the bending moment at the next point. Bending moment at B, we can find BMB is equal to moment at B 37.5 into total length 8 meter, 37.5 into 8 minus moment of UDL 10 into 8 into 8 by 2 minus 10 into 8 into 8 by 2. Answer is minus 20 kilonewton meter. Okay. Similarly, moment at C is how much? Moment at C will be 0 only because it's a free end. There won't be any moment. Moment at C equal to 0. Okay. Now you can find you can write the bending moment diagram now. Correct? Bending moment diagram will be, write the reference line. Okay. Now bending moment at A is 0. Bending moment at X is how much? It is 70.31. 70.31. And bending moment at B is minus 20, is below the axis, minus 20. And bending moment at C is 0. Okay. Now draw the BMD now. Okay, this is what the nature of BMD. Okay, as the load acting on the beam is UDL, so it will be a parabolic nature of BMD. Okay, this is what the bending moment diagram. Okay, this is point B. Okay, this is point A, this is point C. Okay, now question is to find suitable cable profile. Correct? Suitable cable profile. What will be the nature of cable profile now? Nature of cable profile will be Draw the longitude down section of the beam. Draw the longitudinal section of the beam. Then draw the central axis. Central axis. Then now here it asked to suggest a suitable cable profile. Okay, what should be the cable profile? It should be similar to the PMD but in opposite direction. I'll read the diagram now. Like this. Okay, this is what should be the nature of cable profile. Okay, so if you want to find what should be the eccentricity at this point and this point, you can find the eccentricity using E is equal to m by p. Okay, cable profile using, if you want to find the eccentricity at those points, no, using this E is equal to m by p, you can find it. Okay, eccentricity at A equal to 0, obviously, because bending moment at point A equal to 0. And if you want to find what should be the eccentricity of the cable at X, m by p, m is 70.31 kilonewton meter, and pre-stressing force is given in the problem. How much it is given? Pre-stressing force 500 kilonewton. Here it is given, you can see 500 kilonewton. So m by p will be equal to Ex. Ex is equal to m bending moment at x is 70.31 divided by 500. 70.31 divided by 500. If you calculate, you will get 0.14 meter. Okay, because 70.31 is the kilonewton meter, 500 kilonewton. So you will get the answer in terms of meter. In terms of mm it is 140 mm. 140 mm. Okay, then if you want to find eccentricity at point B, okay, at here if you want to find the eccentricity, you substitute the corresponding moment at B. Moment at B is how much? It is 20 divided by 500. 20 by 500. 20 is, the answer is 0.04 meter, nothing but 40 mm. So you can mention that eccentricity in the cable profile. 140 at X. This should be 140 mm. Here eccentricity should be how much? 40 mm. So this is what the suitable cable profile to counteract the external loads. Okay, this completes the problem. If you have any doubts, you can ask. Any doubts here, students? Thank you. Yes, any doubts? Okay. Next problem. And this particular problem, it is similar to one of the previous problem. Okay, let me go through it. Okay, a pre-stressed concrete beam supports an imposed load of 4 kN per meter over an effective span of 10 meter. The beam has a rectangular section of 200 by 600. Find the effective pre-stressing force in the cable if it is parabolic with the eccentricity of 10 mm at the center and 0 at the ends for the following conditions. If the bending effect of the pre-stressing force is nullified by imposed load for the midspan section, then we have to find what is the magnitude of the pre-stressing force. For the second condition, if the resultant stress due to sulfate, imposed load and pre-stressing force is 0, then at the summit of the beam for midspan section. I think it is similar to the first problem. Yes, it is similar to the first problem. The difference is here point loads are given, but in the fifth problem UDL is given. Okay, this is the same kind of questions you can see here. Pre-stressing force required to balance the externally applied load. Okay, that is first condition. And to calculate P for resultant tensile stress is 0 at midspan. Okay, same conditions are given here. Same conditions are given here. The quantity, you need to find the magnitude of the pre-stressing force to balance the moment due to load. That is the first question. And if the resultant tensile stress is 0, what should be the magnitude of the pre-stressing force? Let me show the solution. All of you solve. If you get any doubts, anytime you can contact me. Okay. Because it is a similar kind of problem, I am not going to solve. Only the small difference is loading condition. Okay. There, the point load is given. Okay. 2-point load is given. Here, UDL is given. Only the difference will be in calculation of the moment. Okay. Due to UDL, it is WL square by 8. There, for 2-point loading, you have taken it as W into A. Correct? You have taken it as W into A in the first problem. Yes, you have taken it as W into A 90. Okay. The same kind of procedure I have followed. You can go through it, solve by yourself. If you get any doubts, you can contact me anytime. Okay. Now, I'll go to the last problem. Last problem.
Sir, time up, sir.
12:50, na? Okay. Okay. We'll wind up the class and we'll continue in the next class. Thank you.